In the previous session, we had gone through the various STP terminologies involved, like root ports, PPDUs, and etc. So now let's look at the main part of STP, which is root bridge election and building of STP topology. The bridge with the lowest bridge ID will become the root bridge. So what does this mean? Earlier we saw that BPDUs are the heart and soul of STP, and they are the ones that have all the information contained about the local information about the bridge, which is like the bridge ID, port ID, its cost, etc. So once your network comes up, switches forward their configuration BPDUs to all the other BPDUs, all the other switches in the network, sorry, and they compare their neighbor information with local information, and they basically compare a few parameters. The first thing that they compare is the bridge ID. So if a bridge finds that his bridge ID is the lowest amongst all the other switches in the network, then he declares himself to be the root bridge. So the first thing he checks is the entire bridge ID field, that is including the priority and the MAC. But if, as I said before, priority is usually default. If the priority is default, then he checks his MAC. So whichever happens to be the least, then he elects himself to be the root bridge. Now once the root bridge election is complete, the spanning tree starts building its topology. And how does it do? It uses the minimum spanning tree algorithm to calculate a least cost path from the root bridge to all its other nodes in the network. But during this, we may have a case where there are two bridges which can be reached through the same cost. So how is this tie resolved? Or it can also happen that there are two switches which are having two back-to-back links connected, and they'll obviously be having the same cost as well. So how are these sort of ties resolved in STP? So basically, if two bridges offer the same link cost, then the bridge which has the lowest bridge ID gets selected to be the designated bridge, which means that that bridge gets selected to be a part of the forwarding topology of STP. So this is how ties are resolved if two links have the same cost. Now let's see what happens if two ports connected to each other on the same two switches have the same cost. So now the bridge ID factor is also negated, because there are two links between two switches, so the bridge ID is the same. So how is this resolved? So the bridge which has the lowest port ID then gets selected as a designated port. So in the bridge there are two ports, and the one which is having the least port ID gets to be the designated port. Now let's do a small simulation which will give us a very clear picture about root bridge election and the building of topology. So basically here I have a similar setup of 4 switches, and we have a loop here. Well, once you put switches together, as I said before, the switches have STP enabled by default in them. So by now the spanning tree has already resolved itself, it's already converged, and you can also see this port to be orange, which is an indication that this is the blocking port, and the loop has already got broken. So but still, let us look at a few things inside the switch which will give us an idea as to how it resolved itself. Now let me go into the first switch, and let me type the command show spanning tree. This is going to show me the details, the information that this switch contains about spanning tree. And there are various other commands related to spanning tree, but this is a very basic command through which you get to know the basic stuff about spanning tree and its bridge ID, and who is supposed to be the root, and what are the port states of the ports involved in the switches. So as you can see, this guy here has a root ID, which basically this is the MAC address of the switch as indicated here. So he says root ID is his own MAC address, which means to say that this guy himself is the root bridge. So how did he elect himself in the root bridge? Probably this guy's bridge ID is the least when compared to all the other switches in the network. So let's verify that once we go out of this. So here he specifies his bridge ID and priority value, and here he specifies his hello timers, max age timers, and forward delay timers as well. And here you can see when we were discussing about the port roles, the root bridge is supposed to have only designated ports. So the port role here says designated, and port state is in forwarding. So forwarding is a normal operation where he's supposed to forward both BPDUs and data frames, right? So this guy has declared himself to be the root bridge because he had the least bridge ID, and then he has all his ports in the designated state, and all his port states are in forwarding state. So this bridge is fine. He's resolved himself in a proper way. So now let's look at this bridge. We run the same command here, and here we see that he doesn't declare himself to be the root bridge because the root bridge election has already happened, and he's telling you who the root bridge is by this information right here. He gives this information because he knows he's to know who is the root bridge. So as we saw earlier, this guy here, so this guy is the root bridge, right? So his MAC address is the one that you see as the root ID. So root ID is the bridge ID of your root bridge. So this root ID information would be the same across all your designated bridges. So whereas this gives the local bridge ID of this particular switch 0, and then let's see what his port roles are. So as you can see, interface 1, which is going towards switch 1, is in designated forwarding because designated ports are supposed to be away from the root bridge. And then the interface 4, which is towards switch 3, is telling us that it's the root port and it's in forwarding state. So both the port states are in forwarding as it's supposed to be, and then this guy is the root port because he's facing the root bridge, and this guy is the designated port. So things are fine in the second switch as well. Now if you verify switch 2, he's going to show similar statistics to switch 0, except that he's going to show his own bridge ID, but the rest of the parameters would be similar to what we saw in switch 0. Now let's see what's happening in switch 1. Now this switch should be of primary interest to us because he's the one who's having the blocking port, so which is basically resolving loops. So as you can see here as well, he mentions the root ID, which is the ID of the root bridge, sorry, and then he also mentions the cost to the root bridge, and then he says he mentions his own bridge ID. And the interesting thing to note here is this. So one of his interfaces, that is interface 1, which is going to switch 0, says he's the root port and it's in forwarding state, which means that he has selected this port to become his root port. But what about the other port? The other port is in the alternate and blocking state. So this port is supposed to be in blocking state because this is the port that will lead us to a loop. So this port has gone into the blocking state in order to prevent the loop. So this is how STP works. This is how effectively STP blocks loops in the network. But you may be a bit confused about what this alternate port role is, which we actually didn't discuss in our slides. See, alternate port is basically a part of rapid spanning tree protocol, which is the 802.1w, and it's not a part of the 802.1d spanning tree protocol. That's because these switches by default they run RSTP. But anyways, even if the switches were to run STP, the only difference would have been that this would have been in disabled blocking state. I'm sorry, that's not disabled, that's designated blocking. So he would still say his role would still be designated, but whereas his port state would be blocking port. So this is how STP has resolved this network. So you can see how efficiently he has blocked off one of its ports which is causing loop, and he has formed a tree structure, but has seen to it that he has involved all his switches in the network. Now we can start autoplay capture, and we can see how BPDUs are getting transmitted across the network. So this guy is the root bridge, right? So you can see these ping packets which are getting transmitted out of him. So these are the BPDU packets. So he forwarded BPDUs to all the other switches, and they in turn forward it to the last switch. Now let's see what topology change is, and what do we mean by convergence of the tree. So what happens to the tree if a working link or a working port goes down, or if somebody disables, or if there's a fiber cut, then what happens to the tree? So it'll be interesting to see in the simulation as well as to what happens when I physically bring down or shut down a port. So we'll be doing that in the simulation shortly. So a topology change notification. So as we were discussing about BPDUs earlier, we saw that the BPDU has a field which specifies the BPDU type. So in the BPDU type we have one. It says it's a topology change notification BPDU. So when do we have these topology change notification BPDUs? So basically when STP is up and running and the entire network is okay, there's no problem, you usually have these configuration BPDUs running around. But once you have a link break or a topology change that happened, like say an operator, he introduces a new switch into the network, or he removes a switch from the network, or he does a fiber cut, or he disables one of the ports, then you have a topology change, right? Your physical topology is changing. So that's when topology change notifications comes into play. So the bridge which has encountered this problem, he's going to send this topology notification by setting the BPDU type to 1, and he's going to send it to the root bridge. So once the root bridge receives this, the root bridge, he sets the TC and topology change notification flag in the BPDUs, and he forwards this to TC and BPDU to all the switches, asking them for a reconvergence. So what do we mean by reconvergence is that the switches now have to again rethink about the network. They have to analyze how their network is, what are the different paths that they have right now, and which path is leading to a loop, and or which path got disabled, so which other port has to be enabled. So the switches have to take that decision now. So effectively switches make a decision as to if any other switch was added, then the new loop has to be broken, or if existing link went down, then should an alternate path be enabled. So these sort of decisions are taken by switches during the topology change notification BPDUs. So effectively reconvergence happens, and an alternate path to the switch which incurred a failure gets enabled, such that normal operation can resume. So this is how effectively STP automatically it resolves link failures or changes to topology. So let's see that in the simulation as well. So let me stop the simulation, and now this orange port is your blocking port right now. So let me do a link down on this interface and see whether this interface gets enabled. Before which, let's check which is the root port. Yeah, so interface 1 is the root port, and the blocking port is interface 2. So I should be shutting down interface 1. There you go. I've shut it down. Let's see what happens. So these ping packets, which are BPDUs, are now getting transmitted from the root bridge, and as you can see, this link was disabled, right? So he could not transmit it over the link. Now this guy is supposed to get enabled in some time. So there you go. So we had seen this link to be orange, but now this guy has turned green, indicating that the blocking port has now become active. So ideally this guy would now become the root port, because every designated bridge should have a root port, right? So this guy is the one who's facing the root bridge, so this port would be the root port. Let's verify that. Show spanning tree. Yes, there you go. So link 1 is shut down, so he's not in the table. Now interface 2 has become the root port, and its state says it's in forwarding state. So this is how effectively STP has resolved, is reconverged basically. Now coming to the cost of these links, here you can see that he says cost is 19 because he's using a 100 Mbps link. So let me show you. So by default it's 100 Mbps, so that's why he says his cost is 19, as we saw in the IEEE standard metric. Now all of these are 100 Mbps links, so the cost here as well he says 19. But what about the path cost? The path cost to reach this switch from the root bridge would be 19 plus 19, or it's this way now, it's 19 plus 19. So 19 is the cost for the root bridge to reach this guy, and 19 is also the cost for the root bridge to reach switch 0 here. So as these two guys are on the least cost path, they get elected to be the designated router. Now we saw earlier that this guy has the least bridge ID, so he elected himself to be the root bridge. So once he elected himself to be the root bridge, both of his ports should go into the designated forwarding mode. So these two will be DPs, designated ports, and both of them will be in forwarding. So we can see that here he has elected himself to be the root bridge because he has the least bridge ID. And then he runs the MST algorithm to calculate the least cost path, and he finds that this switch can be reached on this interface by a cost of 19, whereas if he goes all the way around it would be 19 into 3. So he chooses this to be his designated bridge and this to be his least cost. And similarly, switch 2 can be reached by a cost of 19 through this interface, else it would be 19 into 3 if he comes all the way around, right? So he chooses this also to be his designated bridge and this link to be his active link, least cost link. So naturally this port will now become the root port, and this port will now become the root port. So we can see interface 4 here is the root port and it's in forwarding mode, and the other interface should become the designated forwarding interface. And similarly here interface 3 is the root port, let me show that for you. Yeah, interface 3 is the root port and interface 2 is your designated forwarding port. And finally coming to this switch, now I was talking about resolving ties previously. So let's see how there's actually a tie here, and when it comes to resolving what port should become the root port, or which path should this switch take when both his paths are enabled. So let me re-enable his interface, which I had previously shut down. let's give it some time to come up so that we can check what was the tie to choose a path to reach this guy, and how did STP resolve the tie. So there you go, this interface has come up. So uh, as it was originally, this port has again turned green and this port has gone back to the blocking state. So this clearly tells us that span tree again has recalculated the minimum cost required to reach this guy, and he has chosen this path. And why did he do that? Let's see why. Let's see how he resolved the tie. So as we know, the cost of this link is 19 and the cost of this is also 19. So it's 19 into 2 this way, but it's also 19 into 2 this way as well. So there's a tie in cost. So the first thing he checked was cost. He found that there's a tie to reach this guy. Now what's the second thing that he's supposed to see? The second thing that he's supposed to see is if there are two paths to reach the switch which are of the same cost, then you're supposed to see the bridge IDs of your neighbors. Whichever neighbor is having the least bridge ID, he is going to get selected to be your designated bridge. So you'll be connected to that guy through the interface. So let's check the bridge IDs of switch 0 and switch 2. Let's see who has the least bridge ID. So according to the topology now, it should be switch 0 which is having the least bridge. So switch ID of switch 0 is this, which is 000A41E9. And now let's compare it with the bridge ID of switch 2. There you go, you can clearly see that the bridge ID of switch 0 is lesser than the bridge ID of switch 2. Priority is the same, so you come down to comparing the MAC and you see that the MAC of switch 0 is lesser and hence the bridge ID is lesser, and thus the path leading from switch 0 was selected to be the designated bridge for switch 1. So this is how basically STP resolves itself. This is how STP forms a tree. This is how he blocks one of the ports in order to prevent loops. And we also saw what happens when we manually shut down this port. He provided redundancy through this link by enabling this from blocking state, and he brought it into the forwarding state. So this basically summarizes the whole working of STP, and this basically summarizes whatever we have learned till now. So using Cisco Packet Tracer, you can build such networks all by yourselves, and you can see how STP operates. So I can also show you a complex network which I had built. So here you have a even more complex network of switches, an interconnection of switches, and you have 4 clients connected to the outer edges of the network. So here when I run the auto capture play, you can see that the BPDUs are getting generated from this guy. So he's supposed to be the root bridge. We can verify that shortly. So you can see that BPDUs are getting transmitted all across the network, and when the BPDUs are received by the PCs, they're discarding them because it's of no meaning to them, but whereas the switches are accepting those BPDUs because that's how STP runs on, so they need to accept those BPDUs. And you can also see that the BPDU packets are being received even on interfaces which are being blocked. Because as we discussed before, it is very much necessary for STP to continuously receive BPDUs every interval, which is known as hello timer, which is by default 2 seconds. So it is important for STP to keep receiving them every 2 seconds on all its interfaces. Now let's stop the BPDU simulation, and I'll show you a small ping or a ICMP packet as to how it travels from one PC to the other. So as you can see, the ping was successful. Let's see how it went through the network. So the blue packet, it reaches switch 5, and then it comes to switch 3, which is the root bridge, because that is the link which is enabled. He cannot go any other way because this link is disabled. And then he comes to switch 2 because this is the enabled link, and that is the least cost available to reach PC1. So on PC1 replies and the message follows the same path back to the source. So you can do such simulations all by yourselves and see how data frames are handled differently to BPDU frames. So we saw that the ping packets were traveling all over the network irrespective of what port was blocked and what port was forwarding, whereas data packets, as you can see, they travel through a specific pattern, through a specific path through the network, and it cannot be pushed through the disabled links, of course. So now we come to the end of this presentation. So let me stop the simulation and go back to the slides. So let's see a few limitations of STP. We've seen how effectively STP worked all this while, but STP has a few limitations of its own. One of the limitations is that if there are frequent topology changes happening in your network, then this can cause a few problems, because STP is constantly sending out topology change notification BPDUs to reconverge its network, during which a lot of your ports are going from blocking state to forwarding to listening and learning. So this takes a lot of time, and during which your STP has not effectively resolved itself. So there may be a case that there are still loops, or there may be cases where there are packets getting dropped because STP hasn't resolved itself properly. So frequent topology changes may lead to problems, and STP takes 30 seconds to go through port state changes. This is because we saw what the forward timer delay between the listening to learning states and learning to forwarding states. So total of 30 seconds STP takes to go through the different states of ports from blocking to forwarding. So by that time your spanning tree would take almost 30 to 50 seconds to converge completely. So this limitation is actually overcome by the rapid spanning tree protocol, which is standardized as 802.1w, and this takes around 5 to 10 seconds. It takes around 5 seconds to converge, because as we saw in one of the simulations, the port state was actually in alternate. Sorry, the port role was showing as alternate instead of being blocking. So the advantage of RSTP is that being in the alternate state, it's almost ready to forward packets. So as soon as it detects a link failure on one of its other route designated ports, it's gonna push himself directly into the forwarding state, and avoiding all of those listening and learning states to come to the forwarding state. That is why he takes only 5 seconds to converge when compared to STP taking 30 seconds to converge. And also in the last part of the simulation, we saw how an ICMP ping packet went through the network. So STP cannot basically do load balancing, because we saw that even though say the packet could have taken a different route through the network, say it could have taken a diagonal route which seemed shorter, but STP took a specific route to the destination because that was the least cost route. So even though that's the least cost route to your destination, if your traffic is always flowing on those links, and it's not effectively managed, because you have a lot of other links which are going down, even though they're of 1 gig capacity, say, they're always being kept down. You're not at all utilizing those links, so you cannot do traffic load balancing. It always follows a single pattern, even though your other bandwidth is free. So your bandwidth is being wasted basically. So this problem is overcome by the multiple spelling tree, which uses a concept of MST instances to do load sharing. And the last limitation is the more number of switches you put in, the more convergence time it takes, because obviously BPDUs have to travel across all the switches and election has to happen, and a larger topology would take obviously more time to converge. So these are the basic limitations of STP. Now coming to the conclusions of the entire session, like we learned how loops are dangerous. So we learned how STP resolves these loops and provide redundancies as well. So these are two main features of STP, and we also got to know how STP automatically resolves and converges during link failures. We did a simulation on that as well, and we saw how BPDUs are the heart of STP. They carry all the information related to STPs and how BPDUs traverses across the network. And we also saw what all improvements and what all limitations were overcome over STP by using the RSTP and MSTP protocols and other proprietary STP protocols. So here we come to the end of this video tutorial. So please do provide your feedback on this video tutorial. Thank you.